Recording in progress.
Welcome back, class. Last week, we discussed the concept of mixed numbers. And what we need to keep in mind when it comes to the topic of mixed numbers is we need to essentially understand the fact that a mixed number exists as a way for us to express our ideas in a simple manner to someone who is doing real work in the world around ourselves. So, uh, an improper fraction, such as 37 over 3. This is some quantity that actually physically exists in the real world. But for a worker, a construction worker, a welder, a guy who's a painter, to actually measure out 37 thirds of a foot would be kind of a painful process for them. And so what we found last week was that a mixed number exists as a way that we can represent these fractions, which are interesting and do obey the rules of algebra, but are otherwise perhaps not as effective in being able to communicate our ideas as, say, a mixed number. So a mixed number primarily serves the purpose of communication. On the other hand, one of the interesting things that we saw last week was that in certain circumstances, it actually becomes fairly simple for us to do basic operations with mixed numbers. So, for example, if you had, say, 5 halves plus 4 halves, and the question is, well, what would this be equal to? And what we saw last week was that just like with ordinary numbers, you can essentially add mixed numbers column-wise, starting with the fractions themselves, permitting that the fractions have the same denominator. The denominator of the fractional terms needs to be the same. And so when you add this 1/2 and 1/2, you get 1. And just like with our ordinary addition process that we've learned since elementary school, we can carry over the 1. So now we have 1 plus 5, which is 6. 6 plus 4 gives us 10, and voila. However, this only works if our fractional terms are actually the same. And unfortunately, in the world around ourselves, that is rarely the case. And in which instance, we kind of are forced to convert back to an improper fraction, do the addition process there, and then convert back to a mixed number, which is overall kind of a pain in the ass. And so we really don't want to do that if it's at all possible for us to avoid having to do so. And this, of course, begs the question, well, if mixed numbers have um, such a small use case, or such a limited perhaps use case, why in the world would we spend a week learning about them? And the answer to that question is twofold. What we need to learn about mathematics in general is that math is a process of improvement continually over the past 3,000, 4,000, 5,000 years. And so, as the world has progressed, as technology has progressed, as civilization has progressed, as the need for ever more complicated ways of being able to represent ideas has advanced, okay, the need for then using mixed numbers and or the need for, say, advancing past mixed numbers, i.e. into what are known as the decimals, has increased. And so it's for this reason that we will, in fact, be learning decimals. So on the one hand, you can say mixed numbers are a little bit limited because, 5 and 3/4 plus 4 and 2/5 is a little bit challenging for us to do, perhaps. But then on the other hand, certain subtraction operations are also rather tricky as well. It's not quite as easy to do subtraction with mixed numbers if some of the fractional pieces are bigger, and it kind of forces you to do a borrowing operation. So then the question is, where do we go from here? How do we get from, say, mixed numbers to the next advancement in mathematical understanding, which is to the uh, positional decimal? What are we going to do? And the answer to this question is we're going to go back to the basics. With everything in mathematics, often the next advancement doesn't necessarily have to do with thinking about the world in necessarily a more complicated manner, but it might surprise students to know that you simply need to go back to the basics, go back to your prior understanding, your base axioms, your base principles, and think about whether something in your base principle could be tweaked in order to further your understanding of the subject matter. And so, in this instance, we're going to think about what makes the ordinary addition and subtraction, multiplication and division representation that we use, i.e., in base 10, so powerful. Starting with the basics, just writing out the number line, we'll see that we start with 0. We go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then once we get to 10, we go back to 0. And then if I want to express the idea of 10 plus 1 using our ordinary base 10 number system, I, of course, just exchange my 0 for a 1, and now I have an 11. I can exchange the 0 for a 2, and now I have a 12. 13, so on and so forth. We go all the way until we get to 20, and then we kind of wrap back around, and we keep going and going and going in the same pattern. And this pattern is, in fact, what makes our ordinary numeric system so powerful indeed. And it is in one of the instances the reason why when we start to then work with fractions, we're simply extending our understanding of, say, multiplication and division processes into the world of fractions themselves, because a fraction is just one integer divided by another integer. And so, surprise surprise, if we want to simplify fractions, it is indeed just simply a process of either performing a sequence of division operations, if you're, say, dividing the numerator and denominator in equal parts, or performing prime factorization on the top and the bottom, and then canceling terms out. Okay, so interesting. But how does that relate to what we learned about mixed numbers? Well, it turns out that a decimal is, in fact, just a type of mixed number, as it turns out. In the year 1110 AD, you see a mathematician named Hescara, who was a merchant that went to Venice and essentially traded to the Venetians Arabic manuscripts, which is where we originally were able to come up with, say, the base 10 number system in the Western world to begin with. And it is from these Arab manuscripts that we said that a man named Fibonacci was able to come up with the addition, subtraction, multiplication, and division operators and the algorithms that we learned in our basic elementary school program, as well as the way to represent fractions, which we learned about in the past couple of weeks. And of course, he does this in the 1200s, if you will. So this would have been the 13th century thereabouts. And from Fibonacci, you see this gradual progression in Western mathematics. In Italy specifically, you see a man named Giovanni Bianchini, rather, who in the 1410s to 1460s comes up with what is known as a table of chords. And this table of chords uses is essentially a compilation of astronomical observations that have been converted into base 10, whereas prior to that point, it turns out that most astronomical observations were mostly recorded using Greek radian measurements, if you will. And so that would have been in base 360 and or base 60. And so to convert those into a base 10 representation, was a real move forward, but still it wasn't necessarily good enough. And so between Fibonacci and Giovanni Bianchini's work, you see a man named Simon Steven emerge, who in the 1540s, specifically 1548, wrote a book called De Tiende. And what this book is about is it essentially took the works and ideas of Fibonacci and Giovanni Bianchini, and it expanded upon them to a general theory of numbers, which to my understanding was the first in the West since the end of the Dark Ages. I could be wrong, but it's my understanding that he was the first to essentially posit a general theory of numbers. And Steven goes on to write in his De Tiende, which I highly recommend students read because it's not very long. It's only like 2 or 3 pages long, and it's frankly not very difficult to read either. So he says a number is that which expresseth the quantity and specifically of something. So a number is that which expresseth the quantity of something. And what does he mean by that? Well, you see, our good man Steven was a merchant. He was from the merchant class in Venice, and in particular, he was from a very, very wealthy silk merchant family. And so his family would travel through the Silk Road. They would collect silk. They would come back to Venice with these fine tapestries, and they would, of course, make a lot of money and make Venice very, very wealthy. And so, because of that, uh, Steven was, of course, promoted to the burgess class in Europe, which is akin to being a knight. So a burgess is a little bit different than a knight in the sense that a knight is a military rank. So you get promoted to the rank of knight by usually serving in the army of a king. And if you distinguish yourself, you're promoted to knight, which is a kind of title of nobility that's bestowed on the peasantry. A burgess is very similar. So if you happen to be a very, very wealthy merchant or a wealthy person in the ancient era, usually a king would start to distinguish his wealthy merchants because, all else being equal, a guy who's able to really, really manage his money is a very valuable member of society, regardless of his class, regardless of his family's background. That is a very valuable member of society. And so it used to be that you would get distinguished for your rank or for your abilities back in the day. And so a burgess was the title that was bestowed on Simon Steven. And so as a consequence of just being in this general environment where he would have been a very educated man, he would have also been rich enough to actually read and or own manuscripts himself at a time where, a single manuscript would cost roughly $100,000 back in the day. So it was worth a suit of armor. It was worth a really fancy car. It was worth a very modest, house, if you will. So in this environment where everything is kind of a utility, a merchant uses numbers to do things. A merchant doesn't think necessarily about numbers in a perhaps a particularly sophisticated philosophical sense. To them, things are as valuable as their utility, meaning, gold, an ounce of gold is only as valuable as what it allows you to buy and or what it allows you to trade for. And so the only reason a merchant would want to collect anything at all and or account for anything at all is because it provides value to that individual family. And so in that environment, a number is simply, to this guy, to a merchant, to a banker, a number is simply just an item that's used to account for how much gold is in his bank account, right? So it's a very straightforward definition. A number is that which expresses the quantity of something. Very straightforward. And so, if you think about whole numbers, such as 943. Suppose we've got 2/10, 4/100ths, and 1/10,000ths. Of course, writing this down on a piece of paper in long format is ridiculous. 943, 2/10, 4/100ths, 1/10,000th. That is an absolutely ridiculous number, right? But it's equally ridiculous to express this number in terms of fractions. So 2/10ths would be 2/10, 4/100ths would be 4/100, 1,000th would be 1/1,000. And so you can see this is kind of a pain in the butt already. And so Steven essentially thinks to himself about the way that a mixed number with tens and or hundredths might behave. You could think $10. Suppose we have 10 ounces of gold and 10 ounces and 1/10 of an ounce of gold, and 12 and 1/10 of an ounce of gold. If you add these together, the whole numbers, of course, add. So maybe 10 and 12 gives you 22. 1/10 and 1/10 gives you 2/10. So it's in this kind of environment where Steven is thinking to himself, this number, the denominator specifically, doesn't actually change. And the only thing here that really happens to change is either your numerator. And if you overflow beyond whatever your denominator happens to be, we will, of course, carry on the calculation to the next column over. And so instead of expressing this fractional form, the denominator of the fraction is not necessarily that relevant when you think about it, because if you have one of these ridiculous numbers and another ridiculous number, such as 854, 3/10, let's say 2/100ths, and another 1/1000th, say you wanted to add these two numbers together, right? How you would do this in mixed number format is, of course, you could line up all of your fractions, which is what he would have done. And if you're going to add column wise, you would add the 1 with the 1, which gives you 2. The denominator of 1,000th doesn't change. If we're looking at the second column, 4 and 2 gives you 6. The denominator doesn't change. If we look in this third column, 2/10 plus 3/10 gives me 5/10. And if I look in this fourth column, I'm now adding regular numbers with regular numbers. So 3 plus 4 gives me 7. 4 plus 5 gives me 9. 9 plus 8 gives me 17. But you'll curiously note that my denominators here really didn't change. They really didn't change in the calculation itself. And they more or less simply stand as a kind of placeholder for the units of measure, the units of a fractional denomination that we might be working with. And so this is, in fact, the clue that leads Steven to the decimal notation. So instead of writing this 943 and 2/10, 4/100ths, 1/1000th as this quantity, it turns out that you can simply write the whole number out in front, put a decimal to represent that you're now working with a fractional quantity. You then take your 2 from your tenths place, you take your 4/100ths, put it in the hundredths place, and you take your 1/1000th and you put it in the thousandths place, just like that. So the number to the left of the decimal, this is a whole value of something, and then the number to the right of the decimal expresses a fractional quantity. But it does so very predictably in the sense that each digit is actually a progression of a unit of measure of 10. So what is known as a factor of 10. You can go from 2/10ths to 4/100ths, and then from 4/100ths to 1,000th. And as such, when we are looking at the decimal places themselves, we actually will write out the decimal place names in the following manner. So suppose you've got a decent sized number, such as the following. Of course, we know that if we are dealing with a quantity 9,593, the fourth digit over is the thousands place. The third digit is the hundreds place. The second digit is the tens. The first digit is the ones. Then you get to your decimal, which is more or less just a placeholder, which demarcates a fraction from a whole quantity. But then to the right of the decimal is the tenths place, because what's happening is what you're going to be representing in this first decimal is the quantity 2 over 10. And then when we shift to the next decimal, we're now representing the quantity 4 over 100 in this instance. And so we are dealing with the hundredths place. When we shift over another digit to the right, we are dealing with the thousandths place. And of course, students might ask the question, well, why are we progressing in bases of 10, in factors of 10 for our fractions? And the answer to that question is twofold. On the one hand, our ordinary base 10 system, what we're used to using, that we've been using since elementary school, and that the mathematicians would have found state of the art back in the 1500s, is of course the base 10 counting system with a positional 0. And so it makes sense that if our whole numbers are progressing in increments of 10, that the fractional units of a whole digit that is itself progressing in units of 10 should be fractions of 10. So if we count in fractions of 10, every single time we move a digit over, we are moving over a quantity, which may then be represented very, very nicely during our addition and or subtraction processes. So for example, if you have, say, 10.53, and say we wanted to add this quantity with 17.42. Okay, and we wanted to know what is this equal to. Well, 10.53, it's just 10.53. And then you're going to line up 17.42 just below it, making sure that every single digit is lined up correctly. You want to make sure your hundredths place is lined up with the hundredths place. You want to make sure your tenths place is lined up with tenths. Your ones are lined up with ones, and your tens place is lined up with other tens place. Okay, but as long as you make sure that that's the case, then what's going to happen when you decide to add these digits together is you will simply add 3 plus 2 gives you 5. 5 plus 4 gives you 9. 0 plus 7 is 7. 1 plus 1 is 2, and you have your answer. Now, when you deal with overflow, so we'll demonstrate in a scenario. Suppose we have an overflow situation where we get a unit of 10, such as right here, where we've got 12.56 plus 29.54. If we are starting with the rightmost column, 6 plus 4 gives us 10. Just like with our ordinary addition process, when you are adding with decimals, as soon as you get to a unit of 10, you can, because you're dealing with factors of 10, your fractions themselves are factors of 10, you can then carry over a 1 to the next decimal place. And so just like your ordinary addition process, every rule you learned in grade school is preserved when you use decimal addition. So you can carry the 1 over to the next column. 1 plus 5 gives you 6. 6 plus 5 gives you 11. Carry your 1. 1 plus 2 is 3. 3 plus 9 gives you 12. Carry your 1. 1 plus 1 is 2. 2 plus 2 gives you 4. And voila, you have 42 and 10 cents, if you will. Now, one of the interesting use cases of mixed numbers happens to be in the fact that it's much easier for us to represent the amount of a quantity, the magnitude of a quantity, or the physical amount of a quantity that you might have, because you can represent how many whole parts you have, and as well as representing the fractional value. So what that means is it's a lot easier for me to compare and ask the question, is 5 halves bigger than, say, 4 halves? And you would be able to say, yes, 5 halves is indeed bigger than 4 halves, because you only have to check whether or not the whole units are actually bigger than the other whole units effectively. And so for a wide range of cases, it becomes very easy to kind of eyeball your numbers and say which one is bigger or smaller. Whereas with a imperfect fraction, improper fraction rather, uh, if you have something like 35 halves and you ask the question, is this bigger than 65 thirds? There are going to be many people that will kind of sit there and think about it for a second. It's not exactly clear which one should be bigger than the other. Of course, you could go through the long division process of trying to figure out which of these improper fractions is indeed biggest. You could also engage in some rounding. So if you kind of round this one up to 40, 40 divided by 2, that gives you roughly 20. If you were to round this one up to 70, 70 divided by 2 is, I'm sorry, 70 divided by 3 rather, is going to be a little bit more than 20. So even using rounding, you would get roughly the same answer between 35 divided by 2 and 65 divided by 3. And so you would almost always be forced to have to dig out the long division table and or long division process procedure and perform a calculation just to be able to compare these little fractions with one another. And of course, this is the main limitations of these improper fractions. But on the other hand, we don't really want to be dealing with a situation where we have to convert back and forth between mixed numbers either. And so the question is, well, do decimals help us out here? And the answer is absolutely. It's rather straightforward to compare decimals with one another. 10.9, for example, would be absolutely greater than 5.2 by simply looking at the whole number part. And you can see that because 10 is strictly greater than 5, it really wouldn't matter what fraction is behind the decimal place. It is simply a matter of looking at the whole number part and seeing which whole number part happens to be bigger in order to determine whether or not 10.9 is bigger than 5.2. However, there are a couple of things we have to watch out for. Unlike with regular numbers, with decimals, the farther to the right a decimal happens to be, or said another way, the more trailing zeros occur after that decimal place, the smaller and smaller a number happens to be. So for this instance here, we're at the tens, hundreds, thousands place. So we would say that this is 93,000 thousandths. Okay, and that would literally represent 93 divided by 1,000. So, but if you count the spaces to the right of the decimal for the top decimal, you've got tens, hundreds, thousands, 10,000. So now this number represents 93 10 thousandths. So 93 over 10,000. So roughly 10 times as small as the other number that you were dealing with. Okay, 10 times as small simply because you have another zero here. So you need to count the zeros and see which one is effectively bigger by just looking and seeing, hey, this one has less zeros, so it must be a bigger number. Now, that's the opposite of what you would do with your regular counting system, right? Like you would say 93 followed by 3 zeros is strictly greater than 9,300 because the number of zeros represents this gigantic quantity. In this instance, it's 93,000 on the left-hand side, and on the right-hand side, we have 9,300. And I'd rather have $93,000 in my bank account over $9,300 in my bank account, all else being equal. So we just have to watch out for that little nuance, okay? Another thing we have to watch out for is what happens whenever we decide to introduce negative numbers into the mix. So if we have, say, negative 175.16 and negative 175.17, and we ask which of these is bigger, it's best in many instances when asking the question of which is bigger to always draw out a number line, place a zero somewhere, and then along the number line, you would, of course, travel negative 175.16 units to the left, because that is in the negative direction, and you'd place your negative 175.16. And then to the left of that, you would have negative 175.17 because negative 175.17 it is a smaller number than negative 175.16. Or said another way, it's more negative perhaps than negative 175.16. Now, when something is more negative, we know that a negative number often can be used to represent debt. And so in the real world, all else being equal, you would rather have less debt on your balance sheet at the end of the month. So if you owe a guy $175.16, that is absolutely less than owing someone 175.17. And so even though 175.17 is bigger in magnitude because what we're representing with the negative sign is debt, we would actually prefer numbers that are closer to zero. Or said another way, numbers closer to zero are bigger than numbers that are closer to negative infinity. So we would say negative 175.16 is a bigger number. On the other hand, if you were dealing with decimals that were both positive, so let's switch this up. You would say the reverse. The number that is closer to positive infinity is, in fact, a bigger number in that instance. And that's a little bit of a weird little uh, brain teaser, but it's often one that is used in many, many, many different math textbooks to trip students up. Is to just ask them which number is bigger, and then slap a negative sign in front of some number, and that always seems to trip students up. It doesn't matter which class I happen to be teaching. Now, the next thing that tends to trip students up is whenever you ask them to round to a specific decimal place. It turns out that one of the important reasons why we would want to use the decimal over, say, a mixed number happens to be that similar to a mixed number, I can actually go into the real world and do something useful with a decimal. But more than that, with a decimal number, I actually know when I might be dealing with a kind of ridiculous answer. So, for example, you might have a carpenter, and he performs a calculation, and out of this calculation comes all of this nonsense, okay? And perhaps we are measuring in inches. So the carpenter, he's going to have just a measuring stick available to him for the most part. Um, there aren't very many carpentry tasks that requires super high precision instruments. I suppose some carpenters do, but most don't. And so what the carpenter has here is a little bit of a situation. While he certainly would have the ability to measure out 91 inches by simply stacking his ruler up, maybe across the surface of whatever he's trying to measure a number of times, and just, being very careful to, keep track of like tick marks and lining up his ruler correctly. But it would be fairly straightforward to measure 91 inches or what was approximately 91 inches. But while one would likely be able to measure a tenth of an inch. And it's possible that the carpenter could spend all night, carefully examining his ruler, carefully examining his measuring tape, and perfectly denoting 100 little tick marks per inch. It's incredibly unlikely, in fact, improbable, and more importantly, impossible for the carpenter to measure out a thousandth of an inch. For some perspective, a thousandth of an inch is roughly the thickness of a sheet of paper. Okay, and so a thousandth of an inch is very very thin. It's nothing. It's basically nothing. Okay, so a carpenter can measure in hundredths of an inch, maybe, but thousandths of an inch, that would be a very challenging task indeed. And everything to the right of a thousandth of an inch would simply be impossible. And so for that reason, for this reason alone, usually in math and science and engineering, you're going to have what's called three significant figures of accuracy, because in general, whenever we take a measurement, whatever unit of measurement we use to make a measurement, you can generally only take 1,000th of the measurement device that you're using. Okay, in terms of precision. And that's all that's even possible physically. Okay, if you decide to use inches, it's really physically only possible for most tasks to measure to a thousandth of an inch. And that wouldn't even be possible for the carpenter. But is it possible for if you have high precision tools? Can you do it? Yes. Okay. Would it be possible for the carpenter if he just has a ruler? Probably no. And so in math and engineering, we're going to use three significant figures because we're assuming that we have those high precision instruments available. But for the carpenter, he might only have 2 digits of precision, which would have been considered okay for back in the day. That is pretty dang good. Now, everything, on the other hand, to the right of a thousandth of an inch is basically just nonsense, because if you can't measure it out physically, it's almost like it doesn't exist. We can't even see 8/10,000th of an inch with our eye. We certainly can't see 9/100,000ths of an inch. Okay, at that level, you're like the size of a bacteria. So, there's just no way in heck that you're going to be able to measure that out at scale. So all of this is going to need an adjustment, and that adjustment is called rounding. So usually in a rounding style problem, they're going to tell you round to the nearest thousandth, round to the nearest 10,000th. And we're going to have to be able to recognize which digit we need to round to. So whenever in doubt, just label the digits out. Your fourth digit from the decimal is your 10th 10,000ths. Your fifth digit is your 100,000ths. And there usually aren't any problems that are bigger than that. Okay. So as long as we have a cheat sheet somewhere with each one of these decimals labeled, whenever we're given a problem round to a specific digit, we can do this. So if the question told me round to the nearest 10,000ths, so round to the nearest 10 thousandths. All I'm going to do is I'm going to look to my 10 thousandths place, and then you need to look to the place that's exactly to the right, one space. In this instance, we have a 9. 9 is bigger than 5, so we know we need to round up. We are going to round up by first lobbing off this 9 and then adding a 1 to our 8, giving us a 9. So our new answer is 91,499. And that's pretty good. Interestingly, if we said round to the nearest 10th, because perhaps we simply lacked the ability to measure accurately, and we had the previous measurement. Looking at the tenths place and the number to the right of the 10th, you see we have a 4. 4 is strictly less than 5, and so we will round down. Everything to the right of 4, including 4 itself, simply becomes 0, and our answer is 91.1. Be very careful when you guys are entering your answers into MyLab Math. MyLab Math, for whatever reason, likes to say that students have a wrong answer just because you have a bunch of zeros, and the MyLab Math platform doesn't like that for whatever reason. So just be careful. I am warning you once here, okay? All right, so that is rounding with decimals. We know how we can compare decimal sizes. We can add with decimals. But what about subtraction with decimals? Okay, so subtraction with decimals and or mixed numbers can in fact be a little bit trickier. If you have 10 and 1/10 and you're subtracting 10 and 2/10, what's going to happen is you would start off by saying, well, I can't take away 1/10, I'm sorry, 2/10 from 1/10. And so you might decide that you want to borrow, say, a 1 from this 10. And knowing that a 1 is the same thing as 10 over 10, you then add 10 over 10 with 1 over 10, giving you 11 over 10. And of course, your new problem becomes 9 and 11/10 minus 10 and 2/10. Of course, when you go to do the math, you do 9 minus 10, giving you -1, and 11 minus 2 gives you 9. So you have -1 and 9/10. Unfortunately, this is a wrong answer. Okay? Unfortunately, this is actually a wrong answer. What you actually have to do if you are subtracting mixed numbers and one of your mixed numbers happens to be bigger and you know it's going to give you a negative number is that you're actually going to reverse the order of subtraction. You're going to make a little bit of an adjustment. You're going to do 10 and 2/10 minus 10 and 1/10. And when you subtract these quantities, now you see that you only have 1/10 left over. And because you're subtracting 10 and 2/10 away from 10 and 1/10, what would really happen here is that you would need to slap a negative in front of the 1/10. Hmm. So you just have to watch out with mixed numbers and make an adjustment whenever you start encountering, say, negative numbers with mixed numbers. But because the decimal system is simply an extension of mixed numbers, if you were to go and, say, subtract 10.2 from 10.1, what's going to happen is a very similar thing is going to occur. If you started your subtraction on the right like you ordinarily would, of course, you would have to borrow from the tens place, borrow from this tens place, give yourself an 11. 11 minus 2 gives you 1. And then you've got what is effectively 9 minus 10, which is -1. And so you have the exact same issue that emerges with the decimal approximation, because of course a decimal approximation is just a different way of stating a mixed number. So of course it makes sense that this would be a limitation. In fact, it does make sense. So then what can we do? Well, if we are to take away 10.2 from 10.1, uh, we need to either subtract the whole quantities first, or we simply need to reverse the order of our subtraction process. And that's probably easier for us to remember. So if we do 10.2 minus 10.1, that's going to be the adjustment necessary to give us the correct answer. And then we just need to remember, okay, this is a bigger negative number. So more debt, if you will. So this is a bigger negative number. So you're going to have a negative at the end of the day. And in fact, this will be a negative 0.1. I shouldn't say bigger negative number. I know that's going to confuse some students. So I should say that the magnitude of 10.2 is greater than the magnitude of 10.1. So you have more of that something, even if the something is debt. All right, so this brings us to the topic of multiplication and division with decimals. And the question is, what do you do in order to multiply and or divide decimals? Well, with multiplication of decimals, really it's quite straightforward. There are a number of different techniques. I'll show you a number of them just so that you know how to do it when you encounter it. Say you wanted to perform the operation 10.1 times 12.5, and you're like, what is this equal to? All you have to do is you write out 10.1 and 12.5, and you line up the digits. That's step number one. You need to line up the digits. Second thing, slap the multiplication symbol out in front. Third thing, just like you would with ordinary multiplication, we are going to start on the bottom right-hand side, and we're going to do the multiplication process like we ordinarily would. 5 times 1 gives us 5. 5 times 0 is 0. 5 times 1 is 5. Note that while it's tempting for us to insert the decimal and or keep track of the decimal, that is actually unnecessary. Just like you would for ordinary multiplication, you're going to drop a 0 and then carry on with multiplying using the next digit. So 2 times 1 is 2, 2 times 0 is 0, 2 times 1 is 2. Go ahead and drop down 2 zeros. 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1. Add everything together. Get 5, 2, 6, 2, and 1. Now, it's absolutely ridiculous. I hope all students would agree that if you multiply 10 and a minute with 12 and some change, you are never going to get, it's such a ridiculous notion to assume that you get 12,625. And so the question that students have is, well, what do I do now? How do I make this answer look less ridiculous? Because 12 grand is so ridiculous. You'll never multiply 10 and 12 and get 12 grand. That's absolutely astounding. And so the answer is we have to make an adjustment based on the number of digits. So we count up the number of digits that are behind the decimal place. And in this instance, for the top number, you have 1 digit. So I'm going to keep track of that. And then for the bottom number, I have another digit. So in total, I have 2 digits that I have to account for. And so you're going to take your number, in this case 12,625. You're going to then move a decimal place 2 digits to the left. And your answer is 126.25. And that is how you make the adjustment. Now, there is a reason why this adjustment works, and it has to do with multiplying and or dividing by factors of 10. So please note that whenever you take a number and you multiply by a factor of 10, it's almost like slapping an extra 0 on the back end of a given number. But similarly, whenever you take a number and divide it by units of 10, factors of 10, you're doing almost the exact opposite. And so how this works is really what you've got is you've got 10 and 1/10. And this is being multiplied with 12 and 5/10. And so the adjustment is taking care of what is going on with this 1/10 and 5/10 piece here. And so that's really why you have to make this adjustment. Okay, you have to remember you've got this little decimal, and it turns out that if you're multiplying with one decimal, then that decimal place, just because it exists, you're going to need to adjust by one position to the right. But if you have two decimal places in this instance, or two decimal digits rather, which is what we have here, where we've got 10.1 and 12.5, now we need to make a second adjustment to our mathematics to account for that. Okay. Now, in terms of division with decimals, suppose you wanted to take 20.5 and, I don't know, divide it by 10.3 and ask the question, what is this going to be? It turns out that for the same reasons that if you simply multiply a number by a factor of 10, you can shift it to the right one place, and or if you divide it by a factor of 10, you can shift it to the left one decimal place. What happens whenever you divide decimal digits is it actually is equivalent to if you were to shift the decimal by a single decimal place. And that would be equivalent to like multiplying the top and the bottom, in this instance, by 10. So if you multiply 20.5 by 10, that's going to shift this decimal over one place. You would now have 205 in the numerator. And if you multiplied the denominator by 10, this 10.3 by 10, you would have 103. Ergo, turns out that this is going to be a much easier value to work with for a number of different reasons. On the one hand, once you have something that looks more akin to a regular fraction, there are many instances where our fraction rules will then kick in. It's always possible, for example, that 103 has some sort of common factor that might divide 205. It may also be the case that just by working with numbers that are not decimals, we can in fact use some sort of division process that'll make our lives a little bit easier. And so, for example, we could try in this instance to divide 103 into 205. And 103 will in fact go one time into 205. 1 times 103 gives you 103. And if you subtract 205 minus 103 should give you, well, 5 minus 3 is 2, 0 minus 0 is 0, and 2 minus 1 is 1. So 102 as a remainder. So you've got 1 and 102 parts from 103 as your remainder. So if a mixed number was all you cared about, then this was your winner chicken dinner. But because we are now dealing with decimals and we actually don't care about mixed numbers because we know how much of a pain in the butt they are, what we can do instead, once we get to this 102 point, is we can actually drop down an extra 0. And so now we can repeat this process, but instead of asking ourselves how many times does 103 go into 102, we'll ask ourselves how many times 103 goes into 1020. Okay, and I would estimate that it goes exactly 9 times, and I would hope it goes 9 times. 9 times 103. I'm going to go to the side of my page, do this calculation real quick. 9 times 3 is 27. Carry your 2. 9 times 0 is 0. Plus 2 gives you 2. 9 times 1 is 9. So we get 927. Borrow a 2. Or I'm sorry, borrow a 1 from your 2. We got 10 minus 7 gives us 3. We have to borrow from our 1000 over here. We've got 11. What do we got? Well, 11 minus 2, which should give us 9. 9 minus 9 gives us 0. And so it turns out that we now have 93 that we're working with. And our answer is currently 1.9. We could, of course, keep just adding zeros to the end of our original number. So instead of, dividing 103 into 205, now it's 205.00, where we just keep dropping down an extra zero value to help facilitate us calculating a ever more precise decimal approximation. So 103 now will go into 930 some amount of times, probably 8 times if I had to be a betting man. 8 times 3, 8, 16, 24. 8 into 0 goes 0. 8 times 0, rather, goes 0 times. Plus 2 is 2. 8 times 1 is 8. So we got 824. Subtract. Borrow from your 3. 10 minus 4 is 6. You got 2 minus 2 is 0. 9 minus 8 is 1. Okay, 106. And that would indicate that I actually divided by too low of a term, and that's silly me. I guess I should have seen this earlier. I should have divided by 9, and that would have given me 927 again. I'm not sure why I didn't see that. 10 minus 7 gives you 3. 2 minus 2 is 0. 9 minus 9 is 9. So you'd have 1.99 with a 3 remainder. Now, of course, 103 doesn't go into 3, so now you have a 0. Give yourself an extra 0, and you'd say 103 goes into 300 exactly 2 times. And at this point, you have a pretty long decimal approximation, and you can go for however many digits you would want to go for. All right, but be warned, these extra digits don't actually exist if you cannot measure something to exist in the first place. Okay, so this is the tricky idea of what is known as the positional decimal system and or decimal approximation with division. The decimal division algorithm assumes that you can continuously divide material reality into infinitely smaller parts, i.e., you can divide material reality with arbitrary levels of precision and an infinite level of precision. That is simply not true. Okay. You don't get to often pick what your measuring device is. Instead, the application case for whatever you happen to be doing in the world around you is more or less going to determine the level of accuracy that you have within your calculations. Okay. And so to say that, okay, we can calculate these numbers out to the 10 billionth decimal place, while that's true in this mathematical sense of math being true if there exists this like metaphysical reality, in the physical world where we are dealing with, matter that is not infinitesimally divisible, matter that is discrete. It's discretized. It is composed of little pieces. Okay. You cannot continuously divide things into smaller bits. Okay, there is in fact a limit, and the limit happens to be usually, a factor of 3 from whatever your measuring device happens to be. And the limit for material reality, as far as we can tell, is at the very least the Planck limit. So, you start getting past 10 raised to the negative 12, which is really, really small. That's smaller than 1 billionth of an inch if you're measuring in inches, 10 raised to the negative 12. And so, at that scale, the rules of ordinary physics aren't even necessarily guaranteed to continue to exist. And so you start running into a whole bunch of different issues all at once if you're actually dealing with the super, super small. But the same can be, true of the super, super large if you're dealing with infinitely large quantities because you can't actually count up to infinity. You get into the same uh, uh, problems with infinitely large objects that you do with infinitely small objects, just in a different, just at a different scale, obviously. So this is, of course, just our crash course into multiplication and division with decimals. I hope that students have remembered and or refreshed their memory from their middle school classes, and I will see you in class.